One of the types of adaptive filters that we can use using the LMS basic structure to speed up our adaptation significantly is to operate in the frequency domain. From a basic DSP class, you may know that the FFT is efficient enough that it is often better to transform a signal into the frequency domain, compute the convolution by multiplication, and do the inverse FFT rather than compute the convolution outright. Well, in the case of adaptive filters, we're taking advantage of some of that. We're also increasing our adaptation speed by operating with a separate adaptive filter on every single frequency band. This adaptive filter is going to be length 1. It will have just a single coefficient, and it will be complex. So what does that do? It makes the adaptation speed very fast. We have a short filter, and we know that the best adaptation speed we can expect is usually inversely proportional to the filter length. So that optimizes things. And also, with a length 1 filter, we can't have an eigenvalue spread that's been giving us problems in other cases. So if we have a colored input, for example, then we can choose the mu based on just the energy in a particular frequency band, and so the adaptation speed can be much faster. It can be optimal, I guess, for that particular band. So those are some huge advantages of frequency domain adaptive filters. Very fast adaptation, and they operate very well on colored signals. So why didn't we lead with this? Why is this not the most common type of filter used? Well, one of the problems is that when we're operating in the FFT domain, the result is naturally circular convolution. Let me quick review what that means. Typically, if we have two signals and we convolve those signals, filter one with the impulse response of the other, the output will be the length of the input signal plus the length of the filter signal minus 1. So in the case of FFT-based convolution, when we transform x of n of length n and we multiply that by a filter of length n, that means the output is going to be of length 2n minus 1. Well, we don't have 2n minus 1 data lines. We just have n. And when we take the inverse FFT of that output, then we'll only have n points. So where did the extra n minus 1 points go? They got wrapped around and overlaid with our n points. So this is what's meant by circular convolution. The input, which is too long to fit within the FFT, is simply circularly overlaid with the original samples. This is in general a bad thing when we want to do processing of continuous signals. So what can be done? Well, the first thing we can do is we can try to make sure that our output isn't that long. One of the basic ideas that's done in FFT convolution is that the input is computed, or n samples of the input are zero padded. In other words, zeros are added to them to turn an n length input into a 2n length input where the second half are zeros. If this is done with both the input signal and the filter, then their product in the frequency domain will still be length 2n, and when the inverse transform is computed, the IFFT, we have a 2n length signal, and it's holding a 2n-1 length filtered output. And so there's no circular convolution there. Then when we do our next n samples, we'll have to overlap and add them to the trailing end of our output signal. And that will give us a perfect linear convolution of the two signals. So we can do that here. We can zero pad this to length 2n and that to length 2n. The problem is our adaptive filter W is now going to be 2n in size. And so the output, which we were hoping would now fit within a 2n length FFT, is now going to be essentially 3n-1. 2n for the inverse transform, or the length of the filter W, and n for the filter block size for x of n. So this is another problem. What do we do about that? There is a fancy architecture that involves transforming back and forth several times to make sure everything is the correct length, and that ensures a perfect result. But it gets to be a little bit complex or complicated. Alternatively, we can just live with the problem, and that's what's usually done, but we can do something else to make it a little bit better. And that is, we will do a tapered window on our input vector, and then we will do overlap add on the output, and the result is that effectively we have a little bit better behavior inside in the weights, and the tapering added to that makes it so that the circular convolution problem is typically not too severe. So to summarize, we will take a block of n samples of our input, x of n, and we will window them with a tapered window like the Hamming window. The nice thing about the Hamming window is it's a raised cosine, and if we add offset versions of it by length n over 2, they sum to 1. That'll be important in just a moment. Next, we zero pad our signal out to length 2n. Compute the FFT, do your adaptive filtering, and compute the output signal d hat. D hat will be computed by taking all of the adaptive filter outputs in order, computing the inverse FFT. And now the inverse FFT will look something like this red filter zero padded shape, only it'll have been distorted, obviously some, and it may still have energy out in this region. So we're going to overlap it with our other blocks at each new time frame. And add, I didn't do that to scale and I apologize, so that when we're all done, we will effectively have a linear convolution output. And then finally, we'll advance the frame by n over 2. So if this is of length n, then our next frame, this dash frame in this example, is begun n over 2 samples later. So this is one type of frequency domain adaptive filters. There are several others, but this gives you the idea that we do have some large advantages, but there are some signal processing details that can cause problems. One other type of adaptive filter in the frequency domain actually sums up the outputs of each of the filtered outputs and uses those to directly try to estimate d of n. I haven't seen that one nearly as much. This is much more common, but you can look in the literature and find many different examples.